Hello. I am recording from home, and in order to have use of both my hands, there's a more sensitive setup I have to have where I cannot show my face. So I'll let you get enough of it during the class so you can just look at this. So we're going to be talking about theoretical probability. I feel like the other sheet that you'll see in the first video kind of dips into theoretical probability a little bit. We're going to go more into detail on each experimental and theoretical and really get a good idea of the difference. So if the difference isn't clear now, it will be as you see, some later lessons. Actually, the assignment we did on Thursday and Friday, or that we will do on Friday, is going to be more making it clear what I mean by experimental versus theoretical probability. So if you're confused about that, what each of those things are, it'll become clearer in the future. But we're going to here say this. So previously, probabilities were based on observing data. So this refers to the lesson in the last video I submitted. We said it was about observing data. So for example, that's where we're drawing marbles from a bag and we don't know what's inside. And you can only record what you've pulled out to figure out sort of what's in the bag or what's the chance that you'll pull something out next, right? Or experimental probabilities. If you ever play any games with loot boxes or crates or anything like that, you've actually encountered experimental probability. As some things drop more commonly than others, you're getting an idea for what you can expect to see in later events, right? So the next time you do get a loot box, you'll notice that I'm probably going to get this thing again, whatever game you're playing. But that's based off of past experience, off of observing data, right? Where maybe in your mind you might think I'm getting this thing a lot, I'm probably going to get it again because it's more likely than something that's rarer, right? And that's probability. Probability is really just the chances of uncertain events, right? So theoretical probability is the probability. This is different, right? This is the probability an event occurs when all the outcomes are equally likely. Now, all outcomes are equally likely. We know this is different from the loot box example I was bringing up, because that's something that is, some drops are more likely than others, right? So with that being said, we wouldn't call that theoretical probability. Theoretical probability is used for more things like a coin flip or rolling a die, things like that. So that's theoretical probability. So for example, if you just give me a second. You may be familiar, sorry about that, should have had this ready sooner. You may be familiar with one of these things. It's a die. No, it's not a dice. Dice is for multiple things. This is a single die, right? You have two dice, but one die. You'll hear me say that a million times. So here we have a die, and we know that every outcome is equally likely. If I rolled, what am I going to get? There's no safe answer, I got a 3, right? Or a 1. Or a 5. And we know theoretically each of these outcomes are equally likely. So theoretical probability is written as a fraction, where we see that here we have the number of ways the event can occur. As the event can occur, divided by the total number of equally likely outcomes. Right? So, how many outcomes are on this die? Well, there's 6 of them, right? And how many of these numbers are odd? Well, there's 1, 5, and 3. So there are 3 ways you can get an odd number. So we can write that as 3 out of 6. The probability of getting an odd number on a die is 3 out of 6. The probability of getting a number that is a multiple of 3, we see the number 3, and we see the number 6. Those are multiples of 3. There's 2 of those. So that would be 2 out of 6. That's not the only kind of die that exists, though. This one has 12 sides, right? So the probability of getting a number divisible by 3, or a multiple of 3, that's 3, 6, 9, and 12. That's 4 out of 12 sides, which also reduces to 1 out of 3. So anyway, yeah, if I wanted the probability of rolling a number bigger than 9, well, that's 10, 11, and 12. And so that's 3 out of 12. Anyway, but point is, we can look at probability of different things. A simple event is an event that can occur. I guess it's just not crazy about this definition. Really, yeah, we could say it's an event that can occur. I guess we could say a single event, right? We'll say a single event. Sorry about that. A single event. Right? So that's rolling a 1. Or, you're right. So I rolled a 5, so I didn't. But this is a 1 out of 6 chance. Something that's not a simple event would be rolling a 1 on this and then a 1 on that. And that's like 2 things happening. No, it's not and. It's a single event. Right? Let's talk about a simple event, so we can talk about its complement event. A complement event is the set of all outcomes that are different. I'll say this. That are different from some simple event. Now, this is some specific simple event, right? So, the probability of rolling a 1 is 1 out of 6. The probability of its complement event, which is not rolling a 1, well, that's the other 5 sides, so 5 out of 6. So the probability of rolling a 1 is 1 out of 6. The probability of not rolling a 1 is 5 out of 6. Now, the thing to know is that any event and its complement event, so maybe one event might be rolling an even, its complement would be rolling an odd. You know, they're different from that event. That's every outcome that is different. Things are always either even or odd. To roll an even is 3 out of 6. That's 2, 4, and 6. To roll an odd is 1, 3, and 5. So there's no overlap, and they cover every possible outcome. So so those are each complement events. Now, let's look at this example. What is the probability you will spin each spinner and get a star? So we look at this, and we think about the number of ways the event can occur. Right? That's what we had up here. The number of ways the event can occur. We see there's 2 ways we could land on a star. So we're going to write 2 here out of the total number of equally likely outcomes. We see that there are 8 outcomes. This one, 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 and this one. There's 8 of them, right? There's 8 spots, so that's 2 out of 8. So 2 over 8 is equal to 1/4, right? Next, we have 2, 1, 2, out of 1, 2, 3, 4, 5, 6 outcomes. So note, I included those 2 because that's one of the likely outcomes. So it's 2 out of the 6 possible outcomes. And so we can write 2 out of 6, which is equal to 1/3. Right? So which spinner has a greater probability of getting a star? Well, it's this one. And some of y'all said in my classes because this is a bit of a bigger section. And that is true. That is logical. You can say that. But the focus I want to bring is that this is a bigger fraction than that. We should focus on evaluating. So it's B, right? Evaluating each fraction and using those fractions to understand which is more likely. Because sometimes you'll see examples that aren't as clear-cut as these spinner examples. So now let's flip to the back. You can see some questions. A bag of chocolate candies contains 8 green candies and 16 yellow candies. What is the probability that you would pull out one of the green candies? So remember earlier when we had my spinner, we had 2 stars and either 6 spots or 8 spots. And we think about all the different things that could happen. That was all the different outcomes, right? We can see here that your outcomes could be out of the 8 green candies or the 16 yellow candies. But in all, that's 24 candies. So that's every possible outcome. But what do we want? We would want to pull out one of the green candies. And there are 8 of those. So that's 8 out of 24. If you simplify that fraction, 1 times 8 over 3 times 8. And so those cancel. And we're left with 1/3. I want to show you something if you're still not comfortable with dividing fractions or simplifying fractions. One thing you can do, write 8 and 24 and find a number that divides both of them. So there's 4 times 2 and 12 times 2. You know there's a 2 for both of them. They both divide by 2. And you just keep doing that. So 4 can go into 2 by 2. 12 can go into, it can go into 2 by 6. So we got that and that. And lastly, we have 2 and 1. And that can go 2 and 3. You see these and these, right? On my tree, there's a 2. You see the matching 2s. We're going to cross them out. And who's left on the end? The 1 and the 3. So here, that's going to simplify to 1/3. Next, the spinner below has 4 red, 4 yellow, 4 green, and 4 blue spaces. What is the probability that your spinner will land on a green space? Now we see we have 4, 8, 12, 16 spaces. And We want to know the probability of landing on a green space. Well, we can see there's 4 green spaces. So that's 4 out of 16, which will equal 1/4. If you're still not comfortable with that, you can write 4 and 16. We know 16 is 4 times 4. 4 is 1 times 4. You see the 4 on both of these. Cancel them out. We have 1 and 4, which is 1/4. That's a simple way to simplify fractions. You just write each number and you work out. You may remember doing factor trees. You're just doing factor trees. And you're crossing off where each level has the same number. So 2 and 2, 2 and 2, 2 and 2. Left with 1 and 3. When you roll 1 die, it's not dice. You roll 1 die. What is the probability that you will roll a 1 or a 5? We know that a die has 6 different outcomes. And they want us to know about rolling a 1 or a 5. We know about 2 different possible outcomes. That's 2 out of 6. And you can do it again if you want. 2 and 6. 1, 2, 3, 2. This can go away, and you can't simplify anymore. So you just have the 1 and the 3. So you get 1/3, which is our answer. Okay? So